In this video, we're going to be examining the last two of our gas laws that codify the relationship between pressure, temperature, volume, and moles of gas, starting with Gay-Lussac's law, which describes the relationship between gas pressure and the temperature of that gas. Now, if we increase temperature, we know that temperature is simply a measurement of the kinetic energy that all gas particles have, which means that when we increase the temperature of a gas, their kinetic energy is going to increase, and all of the gas particles in the container being heated are going to move faster than before they were heated. Now, because the gas particles are moving faster, that means that they're going to be moving faster and hitting the sides of the container in which they are trapped with more force, because force is equal to mass times acceleration, and if the gas particles are being accelerated faster because of having a higher temperature, that means that they're going to be pressing on the sides of the container even more, and therefore that means that the pressure of the gas is going to also increase as temperature increases as well. Now, if we get this law in a form of equivalent ratios, we can say that the pressure of a gas and the temperature of that gas are directly related to one another, because if we increase one, the other increases. So we can say that when the pressure and temperature of a gas are divided by each other at specific conditions, the ratio of these two is equal to the pressure and temperature of that gas under different conditions like this. We can use this in order to determine the unknown temperature or the unknown pressure of a gas in two different conditions. So the first thing we observed when we looked at volume and temperature is that whenever our temperature measurements are given in Celsius, we need to do a quick conversion into degrees Kelvin. So if we take 50.0 and add to it 273 degrees Kelvin, that means that we are going to end up with 323 degrees Kelvin is the equivalent of 50 degrees Celsius, and we can do the same for 30 degrees Celsius quickly, in which we find that 30 degrees Celsius is equal to 303 degrees Kelvin, and now we're ready to go. So if we list the initial pressure conditions of our gas, that would be 0.370 atmospheres, or 37% of atmospheric pressure. Since we want to use the SI units of kilopascals, we know that 1 atmosphere is equal to 101.3 kilopascals. So we can do this conversion factor here, and we know that we're taking it as a ratio with our temperature, which is 323 degrees Kelvin. And if we want to find our unknown pressure, P2, we simply need to compare this ratio with the ratio between our unknown pressure and the new temperature, 303 degrees Kelvin. And if we want to isolate P2, all we need to do is multiply both sides by 303 degrees Kelvin. So I'm just going to rewrite that equation like this. So here's 303 degrees Kelvin multiplied by our initial pressure conditions. Again, we'll wait till the final step before we actually put this into the calculator. And then all of this is divided by the initial temperature, 323 degrees Kelvin. And if we check our units, we see atmospheres cancel out because of this conversion factor, and degrees Kelvin cancel out as well because we're dividing two temperatures, leaving the only unit as being kilopascals, which is what we want when we're looking for the final pressure. And if you put this into your calculator, this number will come to approximately 35.2 kilopascals. Now, because we've decreased the temperature from condition 1 to condition 2, we would expect that the pressure would decrease proportional to this temperature decrease as well. And if you actually check what the initial pressure is in kilopascals, that's exactly what we would see. So our final law, you will recognize the name of because it's Avogadro's law, because Avogadro's law describes the simple relationship between the number of moles of a gas and the volume that that gas occupies. So what Avogadro's law states is, assuming that we keep temperature and pressure constant, or temperature and pressure of the gas constant rather, as we increase the number of moles of a gas, which means as we take a sample of gas and we actually add in more gas than what we originally had, well, obviously those particles are going to bump into each other more, and they're going to push each other away, therefore causing the gas volume to increase as well. Again, remember that this is only true assuming that the temperature and pressure of the gas remain constant. That way, the only thing that we're changing is the amount of gas that we have. Now, because these two have a direct relationship with each other, we can write the law as an equivalent ratio as with all of the other ones, where we take the number of moles of our gas, or rather the volume of our gas, divided by the number of moles. We'll see why volume goes on top and number of moles goes on the bottom in the next video. But the ratio of when we take the volume of gas and divide by the number of moles is going to be the same, even if our volume and number of moles are different in two sets of conditions. The ratio between the two is always going to be the same. Now, we can use this in order to calculate what volume we would expect of a specific number of moles of gas if we change the number of moles of that gas. So we start with our initial volume, 2 liters of gas within a balloon, and we're told that this balloon contains 5.00 moles of argon gas, although remember, if it's an ideal gas, the type of this gas doesn't really matter. Now, we know that we're going to add 2.75 moles of argon to our original sample, so if we want to find the total number of moles, 5 plus 2.75 is simply 7.75 moles, and we can use this number in order to find what our new volume is going to be, and we can isolate V2 simply by multiplying both sides by 7.75 moles, which is exactly what I'm going to do here. 7.75 moles multiplied by 2.00 liters, divide by our original number of moles, which is 5.00 moles, and we see that moles cancel, and the only unit that we have left over is the final volume of gas that we're going to have. And if you put this into your calculator, you will get that this number comes to exactly 3.10 liters, and we see that our new volume is larger than our original volume was, which is exactly what we would expect given that we added gas. In the next video, we're going to combine all 4 of the gas laws that we talked about in these 2 videos in order to come up with an ideal gas law that we can use to calculate any of those missing variables, that being pressure, temperature, volume, or number of moles of gas, provided that we have all of the other variables information with us.